Good afternoon, everyone. I'm Liping Zhang, a postdoc at the Chinese University of Hong Kong, working with Professor Wei-Tan Chen. It is my honor to be here today to share my work for this amazing challenge. My presentation title is CLAIR, Self-Consistency Guided Multiplier Learning for Dynamic Parallel MR Image Reconstruction. Let me begin with the outline of this presentation.
Well, CMR is widely adopted for diagnosing cardiac disease due to its exceptional soft tissue contrast, non-invasive nature, and high spatial resolution. Particularly, Cine is the current golden standard for non-invasive evaluation of cardiac functional parameters. And T1 T2 mapping are extensively used for evaluation of intracellular disturbances of the cardiomyopathy. However, these low acquisition, such as the need for repeated acquisition of multiple cardiac cycles for Cine, and the extended acquisition window for T1 and T2 mapping, can cause patient discomfort and introduce motion artifacts. Accelerated CMR addressed this limitation by reducing the number of cardiac cycles and shorten the acquisition window. The data acquisition involves sampling signals in the frequency domain. This process can be expressed as the equation here, where the image undergoes coil sensitivity map projection, followed by spatial FLAIR transform, and finally the sampling pattern. This process is also shown in right figures. However, direct image reconstruction using undersampled data can lead to poor SNR and severe artifacts. So, this motivates us to develop methods that can reconstruct high-quality images from undersampled data.
The objective is to generate high-quality images from rapidly accelerated CMR scans by addressing image digression caused by undersampled reconstructions and motion artifacts.
Parallel image techniques such as grappa and sense are widely used for acceleration in MRI machines. By combining PI with comprehensive methods like KT focus and KT SLAIR, it becomes possible to achieve rapid imaging and higher acceleration rates with improved image quality. Recently, deep learning reconstruction approaches have gained popularity as alternatives to traditional methods. Those approaches utilize neural networks to address the inverse problem by incorporating learnable image K-space across domain pairs. Moreover, some researchers have also explored temporal correlations in the spatial-temporal image domain for dynamic MR reconstruction. This enables capturing and leveraging the temporal information presented in the acquired data for improved reconstruction results.
However, existing approaches commonly suffer from several limitations, including excessive smoothing of reconstructed images, insufficient capture of temporal correlations, limited focus on multicolor CMR reconstruction, incapable of handling highly undersampled multi-contrast CMR images due to reduced original image qualities, neglecting specific challenges and requirements of dynamic CMR imaging.
To reconstruct accelerated CMR, we first formulate it as a learnable multiplier optimization problem. This formulation incorporates a data consistency turn and 3 data adaptive localization turns to effectively constrain the reconstruction in various bays, facilitating high-quality image reconstruction even at high acceleration rates. Next, we propose CLAIR, a self-consistency guided multi-prior learning framework designed to solve this optimization problem. CLAIR leverages the power of unrooted neural networks to exploit spatial-temporal correlations by learning complementary priors in different domains. Moreover, it infers self-consistency learning in the KT domain through end-to-end learning, ensuring that the reconstruction is consistent to the acquired data. This is the overall architecture of the proposed CLAIR framework. We start to briefly introduce the key components of the CLAIR. Details of each component will be illustrated later.
The key components of CLAIR are highlighted in the picture. The framework consists of 4 prior learning steps within each iteration: image prior learning, dynamic temporal prior learning, case-based restoration prior learning, and self-consistency prior learning. At the end of each iteration, a frequency fusion block is utilized to merge the reconstructed results obtained from different prior learning steps. This fusion process leverages the distinct properties of each prior, enhancing the overall reconstruction performance. Importantly, in our approach, we incorporate the joint learning of corneal sensitivity maps along with other components. This joint learning enables the network to effectively account for spatial variations in the sensitivity of receiver coils, further improving the accuracy and quality of the reconstructed images.
We begin by leveraging the spatial temporal correlations present in the color-combined image sequence in the ST domain during each iteration. This is achieved by learning a data-adaptive image prior from the training data. The objective here is to generate artifact-free images and restore the overall anatomical structure from highly degraded images, which enable us to provide complete case-based signals for subsequent dynamic feature extraction and high-frequency restoration. We employ a step of the unrooted gradient descent algorithm to guarantee fidelity to the acquired data and enforce image constraints on the coil-combined images. We utilize UNet to learn a highly nonlinear image prior here. To further capture dynamic features, we propose to learn a temporal prior in the SF domain. This approach takes advantage of the sparsity property exhibited by the signal in the temporal flare domain, arising from the periodic cardiac motion observed in dynamic imaging. Similar to the image prior learning step, we utilize the gradient descent algorithms for ensuring data fidelity and capturing temporal dynamic frequency. We leverage UNet to learn a highly nonlinear dynamic temporal prior here too. Previous approaches have demonstrated that leveraging case-based correlations preserves high-frequency information and enhance image quality. We extend this idea by employing a model in the KT domain to learn spatial temporal case-based priors from multicolor data for high-frequency restoration. The KT CNN comprise 4 convolutional layers that estimate mixing signals based on neighboring data. To ensure consistent signal interpolation in the KT domain, we further incorporate collaboration information to guide K-space prior learning using a collaboration CNN. The collaboration CNN shares the same architecture as the KT CNN and learns scan-specific features from auto-collaboration signals. By sharing network parameters during learning between those two models, we enable the learning of scan-specific features that improve the prediction of mixing high-frequency K-space data. To leverage the benefits of the different priors, a frequency fusion block is introduced to coordinate the feature learning process by merging the reconstructed results from ST, SF, and KT domains. By adjusting coefficients in the equation, the network can balance the contributions from different priors based on their respective strengths and leverage their complementary information for more accurate and faithful dynamic MRI reconstruction. We utilize 2 loss functions, L1 loss and structure similarity index measure loss, to minimize the difference between the reconstructed images and the ground truth images, thereby ensuring accurate reconstruction. Additionally, we applied an L1 loss to constrain collaboration CNN model throughout training. This constraint helps maintain consistent embedding of acquisition features in each iteration, thereby preserving the integrity of the acquired data during the reconstruction process. Well, we evaluate our methods on a cohort of 300 healthy volunteers, which was provided by the CMRxRecon Challenge. To train our models, we used 80% of the available training data and preserves the remaining 20% training data for evaluation. Additionally, we had separate validation and test sets for further evaluation. The data acquisition details for both tasks are listed here. Our team called CLAIR has participated in both the Cine and the mapping task. Number of iterations were set to 12 for all rolling-based models. Network remains consistent for the ST-CNN and SF-CNN, with initial feature dimensions set to 32 for Cine and 64 for mapping. Feature dimensions for KT and collaboration CNN were set to match the number of coils in each respective task. Adam was usage. Models was trained using pattern learning on 2 GPU for mapping task and 4 GPU for Cine task.
For Cine task, the average results on the 20% holdout training data are presented in the top left table. Detailed results for long axis and short axis views, as well as different accelerating factors, are shown in the bottom plots. These results highlight the exceptional reconstruction quality and significant improvement achieved by our proposed method across all evaluation metrics, views, and accelerations. Furthermore, our method also demonstrates robust generalization capabilities for unseen Cine data in both the validation and test sets, as reported in the top right table. These findings demonstrate the effectiveness of our proposed method in achieving high-quality Cine reconstructions. The results of the 10 times accelerated Cine illustrate the faithful reconstructions produced by our method across all views in comparison to other methods. The error maps within the myocardium and the chambers consistently highlight the superior accuracy of our method in rapid Cine reconstruction. For mapping task, the average results on the 20% whole-hour training data are presented in the top left table. Detailed results for T1 weighted and T2 weighted images, as well as different accelerating factors, are shown in the bottom plots. Those results highlight the significant improvement achieved by our proposed method for both weighted images across all accelerations. Furthermore, our method also demonstrates robust generalization capabilities for unseen data in both validation and test sets, as reported in the top right table. These findings demonstrate the effectiveness of our proposed methods in achieving high-quality reconstructions for T1 and T2 weighted images, which can potentially benefit T1 and T2 mapping estimation. The results of the 10 times accelerated T1 weighted and T2 weighted images demonstrate that our method can generate more accurate reconstruction over others, and the error maps consistently highlight the superior performance of our methods. More information for both Cine and mapping tasks is listed here. In conclusion, we proposed the CLAIR, the self-consistency guided multiplier learning framework for faithful dynamic MRI reconstruction. Our approach achieved high-quality reconstruction for both cardiac, Cine, and T1 weighted, T2 weighted images. In the future, we plan to extend this method to other dynamic MRI applications. Thank you for listening to the presentation.